Well, it was 7 weeks ago that we started this series that celebrating the accomplishment of eight people who did 7 research projects where the work was done at Berkeley. So the question, the where is where was the work done, not where are they now or where did they used to be. This is something no other university, no other organization in the world can do. It's a remarkable, one of the unique characteristics of Berkeley that we can do something like this. We're saving the best for last. Andy Yao. Andy Yao is a remarkable person, made a lot of interesting decisions in his life. Among the things, he earned 2 PhDs. One in physics, and it wasn't that hard to get a PhD, so I thought he'd get another one in computer science, based on his wife's interest in computer science, and that got him interested in it as this young field. Not only he has 2 PhDs the hard way, he's also got 6 honorary doctorates, more than anybody else I know. And he's a member of the US National Academy of Sciences, and also he's a foreign member of the China Academy of Science and a native member of the China Academy of Science. And some people, when they get the award, they kind of rest on their laurels and pontificate on all the great things they did when they were young. Not Andy Yao. What's his most recent publication? November 2018 is his most recent publications. He hasn't let this month go by without publishing a paper. It's on archive about the topic we're going to hear about today. With that, I'd like to introduce Andy Yao.
Well, thanks, Dave, for the great introduction. And good afternoon, everyone. It's wonderful to be here. And really, every time I come to Berkeley, I get very inspired. Just this morning, I went outside of the faculty club and walked around the lawn, and suddenly many things came back to me because I'm thinking of the 81 to 1982, and somehow this is a place that would energize one's imagination. And I think for a moment I thought that maybe I should ask Descartes that can he hire me again to Berkeley again. The topic I'd like to talk about is something having to do with what I did at Berkeley 35 years ago, but at the same time, I also like to give a perspective about where's computer science going and what's the current state of computer science. So I'm going to talk about something that everybody knows, that computer science is in a new golden age. And I would particularly talk a little bit on FinTech, which is very representative of what happens in computer science. Why are people excited about computer science today? And essentially, it could be regarded as a meeting of minds between economics and computer science in the digital age. And now to talk about FinTech, of course, there's a lot of glitzy things about finance and so on, but I would, as a scientist, I would focus on the scientific drivers of FinTech. Exactly what are the scientific technologies which make it possible for people to think about doing revolutions in the financial services area. And so this comes from computer science and come from economics, and we like to be a little bit more focused. So it's just on the multi-party computation on the computer science side, and on the auction and game theory on the economic side. And so I would give examples of the fundamentals about the multi-party computation and the auction with some illustrations. And then I'm going to show that how these can be, they can come together in one of the hot subjects of today, namely the blockchains. And I'm going to actually focus on a little small corner of the blockchain design and see how auction comes into play. And of course, I will conclude it afterwards. So, but let me start with some reminiscences of of my Berkeley year. That's from 1981 to 1982. And firstly, there are many wonderful colleagues, and some of them are here today. Dick Karp, Bill Kahan, Manuel Bloom, Dave Patterson, Carlos Seekins, and many others. And I'm particularly grateful to Dick Karp, who hired me for that year. And also, I think it was also a wonderful time at Berkeley for the point of view of graduate students. When I came there, Shafi Goldwasser, Sylvia McCarty were both graduate students, and Umesh and Vijay, the Vazirani brothers, and there are Mike Luby, there are Narendra, there are I think almost all the graduate students in that class when I was here, I think they came to be big stars in computer science or in business, and so for me, and mainly that's a very exciting time because it's the dawn of the complexity-based modern cryptography. Because cryptography used to be a exclusively government affair in diplomacy and military applications, but somehow in the 1980s, with the beginning of the distributed computing, the personal computer, suddenly very far-sighted people could envision electronic commerce, and therefore bringing the cryptography into applications that would one day influence people's lives. And the old cryptography doesn't work. If you stick to the old paradigm, you cannot do anything in the modern electronic commerce. And so the complexity-based cryptography is one that gets out of the classical framework. So even I think that the way I look at it is that the transition from the classical cryptography to the modern cryptography can be described as escaping from the shadow of one giant, namely Claude Shannon, who at that time was the reigning theorist of his theory was the reigning theory in cryptography, into the lap of another giant, Alan Turing. Mainly that one has to give up the warm home of Claude Shannon and go into a bolder, a entirely different concept of security that make modern electronic possible. So I will. So that's what makes the intellectual atmosphere at that time so exciting, and Berkeley was the place to be for that subject. And now that's the pre-cafe days. I think there are not as many cafes. I mean, even in California, let alone in places like Princeton or Illinois or some other place. And so all we do is that we just sit outside the lawn and talking about life and work. And I remember that the Umesh Vijay Vazirani brothers, and they were fond of soccer, so they were frequently absent when we were Shafi and Sylvia were talking about things. But at 4 or 5 o'clock, they would come by after their session in soccer, and they join us to discuss things. And so a lot of time have passed, but the fond memory and friendship is something that we always cherished. And that was a most inspiring time in my career, actually I wrote 3 papers during that year. The first one is about the Dolev-Yao security model. I think that it is the beginning. It initiates the symbolic formal security model, which has been growing to a very big subject. And so that's not a complexity base. That's a kind of a formal language based model, but for software and so on, it's much more convenient. And the second paper is about pseudo-random number generation. Pseudo-random number is an old game that the statisticians have done for many years. They are invented many statistical tests. And suddenly cryptography demands that you shouldn't rely on this statistical test, because you can never predict what the hackers are going to do to break the crypto system. So therefore, what would be the appropriate pseudo-random number generation? And so this paper gave I think it's the first satisfactory answer to that. And then there's a paper about multi-party computation that we'll hear a lot more about. And now, so Berkeley is such a wonderful place. Why did I leave? I think that's well, it could be a mistake, I think. But I mean, if every year I can do as much as I did at Berkeley, I think that I would be a really happy person now. But realistically, I think the commuting between Berkeley and Palo Alto many days a week is a little bit difficult. And especially, I like to think about kind of problems, and if I miss an exit, and in the big traffic, I think a person like me, not only it will waste time, but actually it will be difficult to find my way back to the highway again. And now after the Berkeley year, I made frequent visits back to Berkeley, including a 1 semester sabbatical in the spring of 2014. And there are actually a lot more going on between my work, my colleagues, and the Berkeley Department and Simons Institute. Especially in 2010, I started a new institute called the Institute for Interdisciplinary for Information Sciences, and actually many of the several of the Berkeley colleagues were there. I think Dave Patterson was there, and Dick Harp was there, and also Christo Papadimitriou was there. And so there are in this institute we have quite a bit of interactions and the faculty and student exchange, and we even had a joint postdoc program, and there are frequent visitors. And just this year, Professor Michael Jordan, he gave a keynote speech in one of our forum at the new Turing AI Institute in Nanjing, which is a applied research institute that we established in Nanjing to, I think that one of the leaders in the Nanjing city is here today, and with several other colleagues. And just maybe 2 weeks ago, or 1 week ago, that Professor David Patterson received an honorary doctorate from Tsinghua University, and this is the first one that is affiliated with the IIIS. And also during these 6 to 8 years, we have several new recruits in our institute that are affiliated, either graduated from Berkeley or were postdoctoring at Berkeley at one point. And also Shafi invited me to go to a crypto workshop in the Bay Area for next January. So I think the time certainly goes by, but the lasting friendships and cooperation between us grow ever stronger with time. And now, before leaving the reminiscence, I would also particularly like to point out that the modern cryptography didn't come in a total vacuum. Aside from the application demands of a theory, it's only made possible because there are some other things that happened at Berkeley that make it possible. The famous NP complete theory that were established by Cook and Karp, and I think that intractability was really the foundation of all the modern cryptography. So I would like to thank Dick for creating an atmosphere in Berkeley at that time that make us all. I guess I was still a youngster at that time. We all youngsters. We all strive to fulfill the promise of the Berkeley. And so now let me say a little bit about the current the current status of computer science and the future possibilities. And of course, we know there are computer science get into the news nowadays quite often. Really stunning news, not just for computer scientists or even just scientists, but really for everybody to marvel at. And these things really are going to really transform the world. And so the question that people often wonder is that this is a new golden age for computer science, and the answer is emphatically yes. And computer science is breaking news, new grounds everywhere. And Dave Patterson gave a talk. It's a new golden age for computer architecture at the Tsinghua University, and I'm proving a more general theorem, saying that it's a new golden age for everyone. So it's so obvious that I will not really elaborate on it, but let me ask two kind of deeper question, is that why is it any different from the internet and from the personal computer? And computer science has golden age before. Is this any different? And does it have deeper implications? And my answer will still be yes and yes. And why is it that we will have something qualitatively different from the past golden ages? So let me tell you, I mean, this is my personal opinion, and I think it's really the confluence of three trends that happen to arrive at the same time. The first is many years of the computer science research accumulation. I would say that the first 50 years of computer science research is inward looking. Is that the computer scientists are just getting started, and we are just trying to strengthen ourselves by making computer run faster, organize better, and so that we can serve other people better. So in this 50 years, we are sort of below the radar, and people would only talk about us when they praise us for saying that, oh, the computer scientists have made things 10 times faster, and it's wonderful for me to have this processing power, and we during those 50 years we're just accumulating knowledge, just doing things without trying to show the world that we intellectually somehow have a lot of things to say. And so that's the first trend. After 50 years, hardware, software, and even AI, and now suddenly we possess really a lot of power. The second trend is the maturing of the interdisciplinary sciences. I still remember in the 1990s and early 1990s, for a while, I also got fascinated with computational biology because it's really seemed to be the big things to go. So not only computer science with biology, and then there's this quantum computing, and then there is mechanism design. So for the last 30 years, I would say that people work very hard in trying to create interfaces between different disciplines. And initially, it seemed to be impossible. Certainly, I think the computational biology early days was pretty rough. But somehow, at some point, it became really fruitful, and people feel very comfortable, and led to the situation today. You can see that in many areas, people from different disciplines can work as a team, and do wonderful things. So it's that this 30 years of creating interdisciplinary interaction make computer science to be better understood, and also can show that we are not just a raw supercomputer, and actually the computational lens, the computational way of thinking also can help in solving problems in other disciplines. And so now I think that it's pretty much matured. And so that already takes us one step beyond from the earlier situation, namely that the interdisciplinary recognition means that we are accepted as a comrade within the discipline of different sciences, and we can do things. And now the third one, which I think is really the coup d'etat, the one that really made computer science to become the way that we all think is the golden age, is that the integration of the sciences through globalization and the science and the industry get into a very close loop of collaboration, and really the new sciences, the new industries, the industries that generate a lot of new innovation, they heavily depend upon the sciences, and in particular about the computer science. I think that makes the world to be, it's almost inescapable that computer science would get into such a visible and a prominent position, and things will just get even better, because the electronic, the progress in information science has a speed bigger than almost any other science and engineering. So computer science will hold more and more in the value chain. So in other words, it will become the case when we can on the end of being able to decide what are the things that would have an impact in the world, and not just waiting for others to ask us to provide something that suits their purposes. And let me just show you some examples. You can see that computer science and plus the other discipline, and then plus the big industries, and you can see that the quantum computer, the artificial intelligence, and the FinTech, and all these have the dimension of computer science and the interdisciplinary partner, and then with the big future industries development, and so very prominent example of why computer science becomes really prominent. But I would in this talk I would focus on the FinTech part and the technology that make the FinTech run. So let me just say a few words about FinTech, the financial technology. What is FinTech? It's to apply advanced information techniques to financial services. And there are general two ways that this could happen. The IT can make the traditional services more efficient. For example, doing the e-commerce, the online banking, and so on. And but the new technology can also enable novel new services, products, and platforms. And the AI and big data can lead to much better market prediction. Robo-advisor can get to the masses, and even more innovatively, that the IT can create new products. It can create something called digital properties, and it can produce blockchains, which might become an infrastructure that many financial services will end up have to depend upon it. And so the scientific foundation of the FinTech, therefore, is that you have from computer science. The main thing is that the distributed systems and the cryptography and AI and big data and the economics, that the auction theory and the mechanism design, all this based on game theory. These are the really scientific drivers. When they collaborate, they enable us to transform the financial service industry. And basically, I think even at this point, I would like to think it as the following: that from the computer science, all this knowledge of making computer run better, organize better, and how to preserve privacy, and so on, this makes it possible for us to create, I would use the analogy, is to create a great body. It's a very healthy body with the organs can perform very well. But I mean, what does the body want to do? And that's something that in economics, they have found out that if you have this body, then if you ask the body to perform certain functions, to do some jobs, then you would be really great, that you can make the financial services much more efficient and much more innovative. And so so this is a little bit different from the traditional way. I think the financial services, they do things in a more or less intuitive way. I mean, you want to organize data as kind of in a almost a natural way that it should be done. And then they ask computer scientists, saying that now we have this problem. Can you design a particular algorithm for us? And so that's the way that is driven by the economists. And I think that right now what's different in FinTech is that computer science is creating this body, creating this infrastructure, and saying that there are a lot of things that we can do. It's almost like we are giving you a computer with a risk set that I think I got Dave's attention. And saying that, well, you can make program on it. We have, and also actually we can collaborate with you, and we can actually design, because since you may not be familiar with how to write assembly language program, we can do it for you. And so it is in this fashion, because we have created a novel, new, well, as Dick today said, it's a data structure in the big space. that we have finally we are able to have a bigger say in the application to the financial world. Okay. So, I'm going to talk about the multi-party computation and auction, and these two elements meet in the blockchain and expected to play a vital role in FinTech. So I'm going to next I'm going to explain the multi-party computation and auction theory briefly. So the MPC is a cryptographic concept proposed in 1982 that allows computation to be done on encrypted values. And using MPC, a number of servers can jointly compute any function without learning the inputs to the function. And so to take a plain example, a group of people can compute their average salary without any individual revealing her personal salary to the others. And another mode is that there are multiple databases can jointly perform compute statistics on the combined databases without actually sharing data. And these are really two modes. That's the purpose for the multi-party computation can be for individual privacy. I think we just don't want some data to be shared, as well as for the industry's preference to protect their property. And we know that the Facebook and the Google, they really jealously protect their data because they are valuable, except of course for a price if you are willing to do it. And let me give you a illustration of in a more vivid way about what a multi-party computation can do. Just tell you this millionaire's problem, which is a very a well-known problem in this area, and it's two millionaires wish to figure out who has more money, and without revealing any quantitative information. So Alice has X millions, and Bob Y millions, and so they would like to compute is X is less than Y, and so what we envision in this is that you have two people sitting next to each other to have a face-to-face conversation. And is there any method you can think of to carry out a conversation between two individuals directly and without revealing anything about X and Y? So does this sound impossible? The answer is yes. If you just take a look at how Shannon would frame this question and would resolve this question, it's easy to see that that in the information theory sense, it's not possible. And so the answer is that, well, it actually is possible if you think outside the box, and if you align Alan Turing to your side, and then it becomes possible. And let me just show you metaphorically how this is actually done. Okay, and so Alice and Bob. So Alice is put n-sealed envelopes in it. So I think their wealth could be 1 million, 2 million, up to n million, and so Alice would put zeros in the first X envelopes, and the rest would put 1 in it. So these are face down envelopes. You cannot see inside. And then Alice turns her head, and Bob would pick out the envelope number Y to see whether the content is 0 or 1. Then, of course, you would know whether X is strictly less than Y. Okay. So, but the problem is that we would like to do it electronically. So Alice and Bob can just send messages back and forth. Okay. And so in order to implement the above program, you first simulate the encryption of 0 and 1 by using a encryption function. So you would encrypt each envelope using a secret key, K1, K2 to Kn. These are kind of probabilistic encryption. So if you look at it, you will not be able to tell whether it's 0 or 1 unless you know the key. So Alice creates this these keys in private and use it to encrypt and send it to Bob. So Bob understands nothing. It's just looks like random numbers to Bob. And now the step 2 and 3 is that we use something called an oblivious transfer primitive in cryptography so that Bob can get one particular key from Alice. So among all the possible n keys, Bob will retrieve one from Alice, but it must be that Bob without revealing why, and Alice, so Alice would not know what y is, and also it must be that Bob can get only exactly one key. So Bob has to make up his mind what y is in order to do it. And the oblivious transfer is a cryptography, a primitive cryptography invented by Michael Rabin, and a user will get exactly one item from database without a beta safe server knowing which item was queried and transferred. So, this allows us to solve the millionaire problem using a standard cryptography primitive. And so the solution just described for this two-person multi-party computation it's now called the Gabor circuit protocol. And actually, people have studied a lot in recent years, trying to make the Gabor circuit more and more practical for FinTech. And now, since its very beginning, starting with the 3 pioneering papers in this area, it has blossomed into a fairly substantial field in cryptography in the last 35 years. And there are many beautiful work done it in different ways to do multi-party computation. And many advances have been made, and because of FinTech, and people realize that only having a blockchain is not enough. You have to be able to do things that involve, that would preserve privacy. And so MPC becomes a very hot subject for researchers again. And as you can see that essentially a multi-party computation can encompass a lot of things. Almost anything you want to do in distributed computation, you can somehow be phrased as the multi-party computation. And now in 1981, 82, we were happily thinking about cryptography and thought about the multi-party computation, but without us knowing, in a different field, people were doing things that very much have a flavor of multi-party computation. In particular, in 1981, there was a paper by an economist, Roger Myerson, which would win him a Nobel Prize. It's about some sort of multi-party computation. So let me tell you about auction and game theory. In an auction, the bidders typically would submit bids, sometimes sealed, sometimes not. But let's say that they have sealed bids, and now one mechanism would be that the auctioneer would declare that the highest bidder win, and of course just accepting the bids with the price on it. And but this is subject to untruthful bids. If I really think it's worth 2 million, then maybe I would just put 1 million because I think that other people may not bid as much. So in auction theory, if you are the auctioneer, you think this is bad. And now a second mechanism is a very famous one. It's the highest bidder still wins, but the price paid is the second highest bid. And now you can see that there's no reason for anyone to lie, because the highest bidder, if he wins the bid, it doesn't matter the detail of his bid. As long as he's the highest bidder, he will pay the same price. So, so the second price auction by Berkeley and gives bidder incentive to bid their true value. So you don't have to lie. You can sometimes design mechanisms so that people is not tempted to lie. And so incentive compatible or truthful mechanism, it's a cornerstone of the mechanism design. I'm going to say a little bit why economists think that it's good to require people to be truthful, and they do it not for ethical reasons. They do it for scientific reasons, and the auctions are used in the very important the financial activities, like the auctioning the bonds and auctioning the wireless spectrum, and also computer scientists really got a kick of auction because the Google, Baidu, they use auctions for, and I think that's the major source for these giants. And so I think that really stimulated computer scientists in the last 15 years to also work in mechanism design and auctions. And now, well, economics, really, I think it's pretty amazing economics can become a science, because when you think about the people with different motives and the complexity of the issues, how can you make any predictions at all? And you can make any convincing story. But I think they found a white knight in game theory. Somehow, game theory make it possible to have some plausible prediction about what people would do. I think that's truly amazing, and we're not going to have a time to expose it to do a exposition in detail. But I will just say a few words. So basically, in game theory, people are playing games. Each one has some input value, say x1 to xn. But they also have a utility value. This utility value is that when people play this game, at the end there's an outcome. And what's the utility of this outcome is each individual cares about. Okay, the purpose of applying strategy is that I want to apply a good strategy, so that that in the end I got very good utilities in the outcome. So in game theory, there is this concept. When you look at the strategy space as a mathematical space, then you define the concept of equilibrium when everybody has a particular strategy. At this equilibrium point, no party can gain advantage by unilaterally modify her strategy. That's what an equilibrium. And so if the game, it's everybody reveals their true value, then what this says is that at equilibrium, people have no incentive to switch strategy. So let's just imagine you have an input, and suppose the input kind of define the strategy in some way, then it means that you really should stick to your strategy. Okay, so the game theory is founded by von Neumann and Nash, and so you know that this is a very important page. Three of the people on this page, they won Nobel Prizes for their work in the game theory or auction theory, and the fourth one I think is even more famous than than any Nobel Prize winner in von Neumann. So it's so there's a very heavy weight about the science behind it. So perhaps let me try to say why the economists care about designing mechanisms that are truthful. In game theory, what you use it in economics is saying that although we don't really know the dynamics of a people playing is very difficult, and in physics as well as in any sciences, but let's try to take a shortcut, and let's just assume that if you have a system that sooner or later, through self motivation, people will come to an equilibrium. So this is true in politics, in the competition among nations, as well as in business. So this is a plausible idea. You're saying that in economics, let's just think about what the equilibria would be for this game. And so perhaps we can guide people, we can design mechanism in a way such that they will guide people into this equilibrium. Okay, and therefore we can make predictions about people's economic behavior. So that's why it becomes very eagerly adopted by the economists. And I'm not sure whether I mean how how much truth there is that it reflects people's behavior. But I think it's a very good handle on something which is almost unhandleable. And now, the reason why the game theory equilibrium applies to auction, resulting in people only care about truthful mechanism, is that they have shown there's a simple way of doing an argument, saying that no matter what game that you use, there is an equivalent one, such that it is truthful. So therefore, when you design mechanism, and if you assume rational player would all come to the equilibrium, then without loss of generality, you can assume that the mechanism that you design is truthful. And so now that's a tremendous help, because you have a huge game space. And now you say that I only care about those that are truthful. And then we are in business, we can study it mathematically in a much easier way. And sometimes we will be able to write them as a linear program in order to do it. Okay. So now I have got rid of the game theory, and I will just talk about auction that are truthful. And now I want to, because both are dealing with multi-party interaction. So let's see exactly what makes the computer science view of it and the economist view of it different. In the computer science view, it's just compute. There are two numbers, x, y, and they are firmly in place. You just want to know is x less than y. And for auction, you can interpret it as saying that Alice has something to sell, and the bottom line is X million, and Bob has some money that wants to spend, wants to buy it at most for Y million. Is there can they make a deal? Can they cut a deal? And now for computer scientists, this computation to preserve privacy is just want to prevent the leaking of the value. Now for the auction, they are interested in some different properties. They actually, what they care is that whether the number that Bob put down is his true intention. Computer scientists cannot, we only know how to design algorithms to perform a computation that somebody wants to do. But we have no way of knowing the intentions, the utility of people, but for economists in auctions, you want people to tell the truth. Okay. So that's why it's different, and more formally, in multi-party computation, you have n parties holding these n inputs, and to compute the function f jointly, while preserving privacy. In economics, in game theory, you have irrational players in the market with their own agenda and utility, and to jointly maximize some goal. It could be productivity, social welfare, and revenue. And the auction we are particularly interested in is to maximize revenues through incentive choose for bid. And so now I'm just going to very quickly give you a sense about auction and to maximize revenue. Let's say that the seller has partial knowledge of the buyer's interest in the item. There is a prior probability distribution F that it knows, and so how should the seller, so the seller is not privy to the exact number, but knows the distribution, and so the rational seller would just asking for a price which would maximize the expected value, and now this turns out to be, you know, that this looks like a totally trivial answer, but actually game theory did a lot of work saying that even though you can do things much more complicated than what I show you, just simply asking for a price and take it or leave it. But the game theory says that this is the best you can do. Now, if you haggle a lot and so on, you cannot do better than this through the equilibrium concept. Okay, and so it's not a trivial theorem. And now, when you have not just one item but n buyers, there are a lot of unintuitive things that could happen. And Roger Myerson in 1981, that's what I mentioned, that exactly at about the same time, he wrote a paper which gave an elegant and complete solution to the one buyer, n buyer case, and which won him a Nobel Prize. And now, but if you go beyond one item, when you want to sell several items to multiple buyers, very complex, and there's no exact solution. I think many people try to do it, but there are no comparable clean solutions known. And theoretical computer science get into the arena about 15 years ago, and injects new concept into this study. If you look at it in the economic literature, I think they love exact solutions. Okay, they love formulas and they love computation, but when things are not exact, they are not sure how to handle it. They don't prove bounds very much about how bad the ratio could be. And computer science is on the contrary. And if something is NP hard, which it is for multi-item case, then we can only do approximation. And so look at it from the point of view saying that if you are content with having approximation to within a multiple, a constant multiple, and what can you do? You can design algorithms that approximate. But from my point of view, actually more importantly, you can look at economic questions from the point of view of this approximation paradigm. And this is the TCS point of view is novel in the sense that TCS will be able to probe more deeply into the structure of the economics. You can, even though you don't know, because the optimal solution, the landscape is very subtle, very complex, and there's no possible way to characterize it. But if you are happy with discussing things on a rougher scale, if you look at all the solutions with approximately optimal solutions and kind of group them together as a whole, then you see some patterns. And you can ask questions that are meaningful economically. So, so one thing that TCS has done is to use the the tools of TCS and the paradigm of approximation to look at the economic structural questions. And another way that the TCS can contribute is to look at the economic questions that the economists are interested in head on. Because when you look at the 1981 Roger Myerson's paper, a theoretical computer scientist would be really surprised to read the paper, which would be an excellent TCS paper. It's something that exactly the dream ideal of what the problem should be, and that the solution is equally beautiful. So in principle, theoretical computer scientists are also good in solving the mathematical type questions that the economists are interested in. So in both of these ways, TCS has made headway. So I'm just going to say that there are, so I just want to highlight the second item because it has to do with Berkeley. And I started working on the auction problem in 2013 because I wanted to supervise an undergraduate thesis project. And so it turns out there's a very nice problem that I was interested in. And then I got deeper into the auction problem, and in the spring of 2014, I spent the whole semester really just thinking about a very hard problem that people were trying to solve, namely that how to find an approximation algorithm for the multi-item auction problem, and I did solve that problem, and so, I mean, that's one more thing that Berkeley did for me, and so there are a lot of work in this area in computer science. I would just say that the knowledge of constructing approximation algorithm is not only just for getting an algorithm, but it gives you economic insight. So the monotonicity problem is roughly the following: that if you have your painting to sell to a richer clientele, is it possible for you to get more money out of it compared to sell it to a poor clientele? And it should be yes. But for multi-item, it's not true. There are people came up with very interesting examples in which saying that even though these people are willing to pay more, but somehow you cannot get more out of it. You get less than the poorer clientele. And however, if you look at it from the approximation point of view, then actually, even though it's not strictly true, but actually you can extract at least a fraction of that of the clientele. And now there are another example is about something the economists are interested in. They have different models for different group of people. If you sell insurance to an older population as compared to you sell insurance to a young population, you presumably you want to use different models in order to do it. So they are interested in two very standard philosophy of what equilibrium means: the dominant strategy and the Bayesian. And in the case of the k-item case, and there are a lot of open problems, and it turns out that if you use TCS methodology, you would be able to solve this problem. Okay, so just to summarize that TCS contribution, you can solve some classical problems of economics, and you can give a different angle to that the economists, they usually don't think that way. And finally, TCS, the computer science point of view, can create new models. These new models would give new applications of auction theory, and this new model, for example, in the blockchain model. So let me go into sort of the last segment, the the, the blockchain, the computer science meets economics. The blockchain is a growing list of blocks, each containing some certified transaction records and linked together using cryptography. It's an open distributed ledger without central control that's resistant to alteration. And if you use cryptography on it, it's an ideal infrastructure for doing all sorts of FinTech activities. Now, the Bitcoin is a special case of blockchain and actually initiated the whole blockchain movement. And so let's look at the Bitcoin fee design. So let's look at this essentially computer science data structure, and which is suitable to act as a open ledger, and people can register their transaction on it so that it will be a real certified record. And now there are two different kind of players in this Bitcoin business. There's the users who have transactions. They want to get into the open ledger to be certified and registered there. And but the users, one transaction is too small and they don't have the expertise to know how to get it into a block. So there is the miners. These miners, their job is to solve cryptographic puzzles, and in order to create blocks so that they can use the blocks to carry a few transactions on it. Okay, so let's think of only one miner and a bunch of users, and the users would have bits B1, B2 to Bn, so they are n users, and using the current mechanism is a pay your bit mechanism. So the miner would put the bits into sorted decreasing order, and the miner has a finite capacity, so he would just finite capacity because the format saying that you can have 1 million bytes, and would take as many as possible from the highest end and until it's full. But this would generate low revenue because people would not want to be at the head of the link. Okay, so now there's an alternative way to do it. Is monopolistic method. I mean, currently use the pay your bit, but in principle you could think of other mechanisms. And so in this mechanism, the miner does the following. It just pick a k and try to maximize k times the bit bk. And so the idea is that the miners would take k winners from the top, but the charge is according to the bottom of the numbers. So for example, in this case, if you pack 3 into it at the price 10, then you create $30. If you want to pack 4 at $7 each, you create $28. And if you look at all the k, you will come to the conclusion that it's best to take 3 transactions to it. And so this is a great mechanism because it's very simple. It's very easy to implement. But the question is, are we better off than to pay your bit? Are the users incentivized to tell the truth about their maximum bit? And now, this is easy to see that this is not always the case. For example, in this case, if the second bidder changed the bits 13 to 6, then you can see that if you take the first 3, you will generate only $21. But if you take 4, now you generate $24. So if you do this, the bidder 2 now pays only $6 and saving at the 40% discount. And so for each bit sequence, let this delta to be the maximum discount among all the bidders. So this is kind of the worst case for this. And the miners would like to be this delta to be not close to 40%, but close to 0. I mean, that's the way to give people not tempted. So last year, there's a paper by Laureate et al. They studied this problem and examined the NP mechanism, and they do experimentally when the number of bidders gets large, then the discount is almost zero, I mean, for many distributions. And the mathematical setup is that the bit sequence is generated from sorting n IID random numbers drawn from a common distribution F. So the theorem we proved just before coming here. So I think I don't know whether I'm giving a good talk or not, but you should appreciate my sincerity. I spent the last 2 months working out this for this talk. So one can show that for any bounded distribution F between 0 and D, as n goes to infinity, the limit is 0. Okay, so it's confirming their conjecture that the NP is pretty good. It's nearly truthful if the number of players is large. And also this NP is robust against other tactics. For example, the user may want to split the transaction into several and putting a small bits and perhaps can get away with it. And also the miners may want to put in some bits or to delete some bits. So this type of thing, NP is also pretty good to be robust against it. Now, it certainly begs the question that, well, can we go one step further actually to be truthful and generate a lot of revenue? So in Laureate et al.'s paper, and as well as actually in an earlier paper in Goldberg et al. In a different context, in the context of, they call it the digital goods auction, they study something called RSOP, and I think that I would just call it MP2. MP2 is just doing the following variation. So I take the original bits, I randomly separate the bits into 2 parts, and let me apply the MP to each part. But this fee, I'm not going to apply to that part, but actually use the number to be applied to the opposite part. And so in other words, this works like a sampling algorithm. So for a part of the bits, you will use the sampled value from the other one to give yours. And so you see, for example, for this one, for the first part is 10, the second part is 7, and now you just switch the bits, and you can get $24. So now MP2 is truthful because you are using a number which has nothing to do with yourself. And now the question is, do you get good revenue? And this is less than 30. And experimentally, Laureate et al. Say that they didn't see any counterexample to the case that the MP2 is strictly less, well, it's less than MP. And so actually it's not this conjecture can be shown. It's not too difficult to prove. So if you compare it, that MP comes out to be pretty good, and support is a possible candidate for the Bitcoin fee. So I think the lesson I want to say is not this is such something that you should implement. It's just saying that there are a lot of interesting questions that would generate. Well, it's just like we are the computer scientists now. We have the permission to build a big building without any requirement from anyone, and so we are free to design things that we think should be good for doing FinTech. And so in the process, we know we can do all parts of design, but they are interrelated. So this gives us a very rich canvas to investigate our theoretical algorithms on this. that's why this is such an interesting enterprise that I believe will hold the future for us. Now let me conclude the spirit of the whole thing. Firstly, this is a new age of computer science. In the previous 40 years, CS mainly focused on internal development, and but in the new age, CS is coming out to be on stage and sharing lights with others like medicine, physics, chemistry to transform the world. And now, together with this exciting phenomena, it also, there's a burden on us. It's a new game that we should be playing if you are not already doing so, both for institutions and for individual researchers. CS research will be evaluated on the impact that can be articulated and felt by others. So individuals and the institution need to rethink how they should proceed. And now coming down even more to my home, that theorists have the opportunities like never before. We should broaden the arena and take the full advantage. And now the final slides, let me just go and look at the very big picture that in all science, that it's exhilarating times. The research breakthroughs come from a lot of places, especially that they come from the fusion of different scientific ideas, because building a discipline takes decades or 50 years. But when you fuse things, you can really see lights and heat immediately. And let me just go over some of the examples. In the modern cryptography is computer science and plus information theory. The FinTech, computer science plus economics, quantum computing, the CS plus physics. And what are the future possibilities? Well, I think that in the future belongs to purely from an intellectual sense. If I have to say, where is the intellectual thrust of the computer science theory is going, I would say computer science theory should encompass a very, very bigger domain, that we should integrate quantum computing, neuroscience, and AI, because I think that they are all have to do with studying the limit of intelligence. And also, privately, I think that we are rivaling nature in this pursuit. Quantum physics is I think, the ultimate miracle of nature. It gives us out this beautiful world, and with this law, which we understood for over 100 years. But now with quantum computing on the horizon, we will be able, hopefully, to perform all the computations or to simulate what nature can do. Because previously, we can only admire. We look at this room temperature, conductivity, conductor theory. We try to make a theory. So, but we never have been able to do it, to simulate nature. So that's the hardware part as for computer science. The hardware part, we should aim at quantum computer, and Dave Patterson would say how to make a quantum computer architecture. Now, on the software side, I think that our brain, it's the miracle coming from evolution. And we all know it comes from evolution, but we don't know how it works. And I say that since our friends doing quantum computing seems to be on the verge of completing their job, I think that we also should complete our job here. We should try to understand how the brain works, how the software works, and I believe the current success of AI gives you some hints, not by what they can do, similar to brain, but what their difference with how the brain works. So I believe that the next 20 years, the best, the most important subject in the theory of computing will be in this big arena and try to make them whole. And I'm sure this is going to generate lots and lots of careers from this. So with this, I thank you.
Okay, I'm sure a lot of people go, but maybe have time for a couple of questions. Maybe this may be the best part of this series is by inviting him to give a talk, he had to write a new paper. So. I think there's a question down here.
I have a comment and a question.
Where are you?
I'm in the back here.
There you go. Hi.
Comment. We don't care about millionaires anymore, only billionaires. Sorry about that. My question is this: should algorithms be required by law, provably to satisfy their specifications, before being put into the cloud or given to an autonomous agent where we have no control over how they're used?
I think I actually agree with the position. I think the more demand we have on algorithm designers, it will force people to think more deeply, and so that we can understand the algorithm better, and to do what kind of regulation should be satisfied in the view of, I think, for important things. I think that for example, as you said, that things like the rampant use of AI, I think this sort of thing, it should be just like the ethics in the biology. I think I have no problem of having requirements of that kind.
The question here?
In the last few years, as you mentioned, there have been a lot of new tools developed for the field of FinTech, like blockchain, cryptography applications, predictive models, and all that. But people have also talked about new applications of new computer science concepts in FinTech. In your guess, would you think that most of the, value to be extracted out of FinTech or new developments that are coming in the next couple of years are going to be coming out of optimizing the tools that have already been created, like blockchain, or out of new applications of new computer science concepts to economics?
Well, I think that it should be a combination of both. So it could be either look at, in principle, things that people have thought about before, but you want to optimize it, or it could be that depending on the application, that you don't need the full generality of the protocol, and thereby can design simpler algorithm for it. And also at the same time, I think that that people can do fundamental research too. Maybe there is a surprisingly powerful way of doing things we have never thought of before.
Any other questions? All right, great. Thanks very much.